Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, more on weathering. We're trying to break rocks down into smaller pieces. That's what weathering is all about. And right now what we want to do is we want to talk about the second half of weathering. Remember the last time we talked about how there's two types of weathering. There's mechanical and there's chemical. And today, chemical. We're talking about chemical weathering. So chemical is different than mechanical in that chemical weathering alters the internal structures of the minerals. It changes one mineral into another. So you start with, chemical A and you turn it into chemical B. Now, they're going to have the same elements, all right, but they're going to be different in the way they're arranged. And that will break it down when it reacts with certain elements, all right? And the original rock decomposes into substances that are stable on the surface environment. So not all of the rock minerals are as stable as others, and that's what's going to happen as they're forming. So when we talk about chemical weathering, there are 4 types of chemical weathering, that we're going to talk about. There's a few more, but these are the big 4, if you will. The first one has to do with water and carbonic acid, and then how granite weathers, how silicate minerals weather. That's important because silicates are the most common mineral you find on the world, and spheroidal, I think that's how you pronounce it, weathering. I know how to write it, but I don't know. So it's about water and carbonic acid. Water is the most important agent of chemical weathering. So by 90%. It's almost all about the water. And water by itself is actually not reactive. Pure water, distilled water, is not reactive. It doesn't do anything. But water is not pure on the earth. And so what happens is when there's oxygen dissolved in the water, it oxidizes materials, rocks, minerals. Rocks containing iron-rich minerals will then oxidize into yellow or reddish brown. So if you get some water with some oxygen, because like rain, right? Drop of water, whoop, it falls through the air. And what does it pick up? Oxygen. And then what happens is all kinds of cool stuff. And then carbonic acid, all right, the other thing it's falling to it is as a drop of water falls down through the air, it also picks up another gas, carbon dioxide. There's carbon dioxide in the air. It's an important part of our atmosphere. And as it falls, the carbon dioxide then dissolves in the water. So the water isn't just water, it's water. Now it's got mixed in with it some oxygen, that's O2 from chemistry class, and some CO2, carbon dioxide. And when you put H2O and CO2 together, then you make this thing called carbonic acid. That's what the symbol is. And it will decay certain minerals because it's acidic. This is the idea of something called acid rain. And when you have acid rain, and in some places of the world are much worse with acid rain, it can affect the plant life. It's killed the trees here. It can do lots of very interesting things. We have some statues in an acid rain area. This is what it used to look like, and now it's completely decayed. So this is, this is a mineral, and it is breaking down into smaller pieces. And this is that mineral calcite, calcium carbonate, and it's found in marble and limestone, and it's very easily decomposed. And you can see the decomposition and what the poor lady looks like now when you have that. So that's that. But that's not just happening to statues. That's happening to any minerals that are out there just in the wild lands, if you will. Here's a picture of the U.S., and to what degree do we have acid rain? Rain, by the way, has a pH in the neighborhood about 5.3. That's where it should be. pH is, if you recall, a scale of 0 to 14, where 7 is perfect neutral water. But it should be around 5.3, so it is already acidic. So it's less than 7. But you don't want to be lower than 5.3. So here in Houston down here, we're at 5.0. Not terribly bad, still green, but up in these areas, you see we've got an issue, don't you? This is where we've got some more acid rain. So that's going to be an issue in some places. So let's turn our attention. So that was carbonic acid and water and how they play a role. Number 2 is how granite weathers. Now granite is a very common igneous rock, and how does it weather? An interesting thing, it's all back to, it all goes back to chemistry, because granite has a number of minerals in it, and the one that's kind of important is this one, potassium feldspar. Now, it's not that you need to write out KALS308 or whatever, but potassium feldspar breaks down with the action of the H ion. If you recall, that's acid again. And then it breaks down into clay, silica, and potassium bicarbonate. Now, clay and silica, all right, silica is SiO2, okay, is crazy stable. And clay is stable, and it remains in the environment. And so most of the soil that we have in the world, we'll talk about soils later, is clay, because clay comes from granite when it's all said and done, and it can make other stuff. It's also important because what's really good about potassium is this enriches the soil. So what's kicked out when you get the SiO2 from this right here, do you see how you get some Ks left over? Those Ks, and they're K ions, they enrich the soil, and then plants need that to survive. So you kind of see how this is a part of the whole Earth systems and the cycles, is that granite produces minerals that are needed for positive soil production. So a little bit more details about this. Potassium feldspar breaks down into chemical weathering and remains unaltered by the chemical attack. So the quartz. So if you recall, granite has a mixture of different rocks in it, or minerals in it, I should say, and one of them being quartz. And quartz just doesn't break down chemically, but it remains. And so what really happens is the quartz, the little chunks of quartz, they make their way to the oceans, and those become our beaches. So most of quartz is these tiny little sand pieces. That's what contributes to the sandy beaches, because they don't break down. They're the sand dunes, eventually turning into sandstone. Sandstone? Sandstone. You get the idea. All right, and then I guess this is out of order a little bit. The iron-rich rocks, we talked about this a little bit earlier. Remember, we talked about, I'll find that sheet here. When this goes actually with this, the iron-rich rocks, this is how we make the iron ores, is there's a chemical action that produce these iron rocks, which are pretty cool, and you can see they're kind of this red color. The next type is acid, And then we talked briefly about acid precipitation, but let's sort of expand on that a little bit more. Not only, remember I told you, you've got the drop of water flying through the air, that's the water, and he picks up oxygen and carbon dioxide, but there's other chemicals in the air. There is SO2, carbon monoxide, and the nitrogen oxides. The X could be like a lot of numbers, like NO1, NO2, NO3, etc. And they can form stronger acids, and they can create all kinds of issues. And like I said before, if it's below 5.6, then it's called acid rain. So thirdly, let's talk about the weathering of silicate materials. So silicate is the most common of all the materials, and then quartz is silica, feldspars, amphibole. This is also related to the granite, because granite has many of these things in them. But the reason we want to talk about it now is because most of the Earth's surface is made of these silicate materials, and they break down, okay, because they're going to break down into these things, and these things are valuable and important when they do chemical weathering for soil formation and ultimately for living things to work. And then lastly, let's talk about spheroidal. I'm not sure I know how to pronounce that. Spheroidal? That's not eel. I don't know. The S weathering. It has to do with the word sphere. They become like spheres, right? You know, get the idea. So what first happens, so kind of draw a picture of this, is that water permeates into a jointed rock. You get a rock with some cracks, right? And water penetrates it, but it's going to have like acids and stuff like that in it, and those will break it down, right? They break down chemically, and then these rocks are all joints, and it breaks them, right? I mean, it chemically changes them, and now they're like dusty stuff, all right? Because they're going through the cracks, and then as the cracks go on, then the other thing, the sediments, they just fly away, and eventually you get up these spherical, I don't know, shapes. Here's a classic one right here at Joshua Tree National Park in California. Interesting picture right there from the national government. And here's how it works. You have an angular rock. They tend to take on a spherical shape, even though it's angular at first, because the corners and the edges become more rounded, because as that chemical seeps into the cracks, it opens things up. And the corners, of course, are attacked the most because they have greater surface area, and that's why it rounds the corners. So it might have been a nice square block at first, and then what happened is the outside gets rounded by the chemical weathering, and if there's a crack, and then they break off, and then you get the cool spherical weathering like we see here. And that's it, folks, for chemical weathering. So we've talked about mechanical weathering and now chemical weathering. We'll see you in class. Because Houston, we don't got no problem.